Hello everyone, welcome to the video on diagonalization as part of the topic in the theory of computation course on cardinality of sets, infinities, and the diagonalization technique. So just to recap what we have seen in the previous video, we saw what the cardinality of set meant. It's just the size of the set for finite sets, and it extends the notion to infinite sets. And we saw how we could compare cardinalities of sets. In particular, we would say that the cardinality of set A is greater than the cardinality of set B, greater than or equal to the cardinality of set B, if and only if there exists a surjective map that goes from A to B. Okay, similarly, we can say that cardinality of A is less than or equal to the cardinality of B if we exhibit a one-to-one map from A to B. Okay, and this gave us way to compare cardinalities. Then we saw what a countable set was. These were sets that had a cardinality that is at most the cardinality of natural numbers. So any finite set is countable, or if you exhibit a one-to-one map from this set to natural numbers, then it's countable as well. So we saw that I mentioned that rational numbers actually form the set of all rational numbers forms a countable set, but surprisingly, the set of real numbers is an uncountable set. Okay, and to prove this, Cantor came up with this very powerful technique called diagonalization, which will also be very useful in this theory of computing course. Okay, so that's the main thing that we are going to see in today's class. So we'll demonstrate diagonalization, okay, using two different theorems. First, we will define what the power set of a set is, and then the first theorem will be proving that the cardinality of a set is not equal to the cardinality of its power set. Okay, in particular, it will be strictly less than the cardinality of its power set. And we will use diagonalization to prove this. And finally, we'll actually prove Cantor's theorem, which is that the cardinality of natural numbers is strictly less than the cardinality of real numbers. Okay, and we'll use diagonalization to prove this. Good. So before we continue, we'll continue by first defining what a power set of a set is. Okay. Good. So given a set A, the power set P of A is defined to be the set of all subsets of A. Okay. So just for an example, if A is the set 1, 3, and 5, then the power set of A is just going to be the set of all these following subsets. So you always have the empty set. The empty set is always a subset of any set. And then you have the singleton sets here 1, 3, and 5. Then you have these subsets with pairs of elements. And finally, you have the entire set itself. Okay. Good. So this is a power set of A. And so here is a simple fact. For finite sets, then the size of the power set of A is equal to 2 raised to the power of the size of it. Okay. The proof is actually very simple, and you've probably already seen this before, but really the proof is just almost this one line. Basically, we're just counting for a given set A, we're just counting the number of subsets of it. Okay, so here we're just thinking of the size of A as being finite. You can think of it as n, for instance. So this is really just a counting exercise. So to form a subset S of A, okay. So for any element of A, there are really just two choices, okay. Either A is an S or A is not an S, okay. So for the number of subsets that you can have is, for each element you have two choices. So for the first element of A, you have two choices, whether it should be in S or not. Similarly, 2 times 2, and so on. And this is for every element of A, and this is 2 raised to the power of the size of A. Good. Okay. Now, here is the theorem. There is no surjective map F that goes from A to the power set of A. Okay, so really what I'm saying is that there is no map, there exists no map F that goes from A to the power set of A and is surjective. Okay, so just a small note. Okay, it's easy to see that the cardinality of A is certainly less than or equal to the cardinality of the power set of A. Okay, so how do you show this? It's you just construct an injective map. So what this theorem is basically saying is that the cardinality of A is strictly less than the cardinality of the power set of A. Okay, and why is that? It's because the theorem tells you that the cardinality of the power set of A, okay, is not equal to the cardinality of A. But we do know that the cardinality of A is less than or equal to the cardinality of power set of A. So this is the strict inequality. Okay, of cardinalities that we have seen in the previous video. Good. So let's do the proof of the theorem. And the proof will actually use, so the proof is actually simple. It's kind of obvious if A is finite. Okay, that's because if it's finite, we know from the fact that the size of the power set of A is actually just 2 to the size of A. And so we know that any number, any natural number n is not equal to 2 to n. Okay, but really the question is, how do we prove this for infinite sets? Okay, we'll actually prove this by contradiction. Okay, so let's say that F be such a surjection, be a surjective map. Okay, so this is, we're going to then contradict it. Okay, so let's say that it actually exists. Okay, now what we're going to do is we're going to come up with a set. So remember what a surjection means. So we have this map that goes from A to the power set of A, and it means that every element in the power set will have at least one incoming arc. Okay, potentially many, but yeah, so these are good. So what we are going to do is we are going to construct a particular set B which belongs to the power set. Okay, so and this construction of the set will be the key step in the proof. Let B be the set of all elements in A, okay, such that X is not an element of f of x. Okay, so this is a key step. Okay, so the set B will be some set inside the power set. Why is that? Well, will be some element inside the power set. Why is that? Because it's just a subset of elements inside A, and any subset belongs to the power set. And what we are going to do is we're going to this set B is constructed in a special way, and then we're just going to contradict B actually belonging to the power set later. So this will end up showing that there can be no set. Okay. Good. So, and this kind of a step where we are constructing this element of we are assuming a surjective map, and then we are constructing an element in the range. Okay. Uh, and the construction is usually somewhat self-referential. This is a common feature in many of the diagonalization proofs. Okay. So now, just by definition, because it's a subset of elements, B is just a subset of A. Therefore, B is just an element, the power set of A, because the power set contains all subsets. Okay. Okay. Now, since F is a surjective map, there has to exist some Y which is an element of A such that Y, f of Y, is equal to B. So what are we saying? So we are taking this B here. Well, B belongs to the power set, so it has to have at least one incoming arc. And let this element from which this incoming arc came in be Y. Okay, so f of Y is equal to B. Good. Now, just by the definition of B, we have that Y is an element of B if and only if Y is not an element of f of Y. Okay. Right? This is just the definition of B. It contains all elements X such that X is not an element of f of X. Okay, so similarly for Y. Okay, so that is Y is in B if and only if Y is not in B. Okay. Now this is of course this is a contradiction. And this proves that there cannot be any surjective map. Okay, this completes the proof. Okay, so the key step in this diagonalization proof is to construct this set B. Okay, and because there exists a surjection, we looked at this element y that mapped to B, and then the main question he asked us was, well, is y an element of B? Okay, we know that f of y is equal to B. This is because of the surjection. Now we ask, well, is y an element of B? And I mean, then if you go by the definition of B, you see that you reach a contradiction. Okay. So this shows that the size of A, the cardinality of A, that is less than, is not equal. Okay. In particular, it is less than the cardinality of the power set of A. Okay. And we prove this by using diagonalization. Now we will show the second theorem, which will be proven by diagonalization. And this is the theorem of Cantor, famous theorem of Cantor, showed that there is no surjective map from natural numbers scripted to real numbers, okay, which we denote by script R. Good. And the proof will be through diagonalization. Okay, so good. So recall that this, by the way, this theorem shows that hence the set of real numbers is not countable. Good. And again, so how do we, so we will show that there is no surjection from natural numbers to real numbers. In fact, we will show something even more particular. We will show that there is no surjective map from natural numbers to just the interval 0 to 1. Okay, remember that the interval 0 to 1 is a subset of real numbers. Okay, and the idea is by diagonalization. And in this proof, after this proof, it will become clear why we actually use the term diagonalization okay, to refer to this technique. So again, let's assume, for sake of contradiction, that there exists a surjection from natural numbers to the interval from 0 to 1. Okay. Okay. So what we will do is we will construct some x, some special real number x, okay, such that there is no pre-image for f, okay, that maps to x. So f inverse of x is really just an empty set. Okay, so there is no element which actually maps to x according to f, and this will contradict the fact that f is a surjection. And we'll actually construct x in stages. Okay. So what do we want to show? We will want to construct this x so that f of I mean, it is, I mean, f of 1 is not equal to x, f of 2 is not equal to x, and similarly, f of no natural number is equal to x. So we'll just do this in stages. So we'll keep ensuring that uh, that all these natural numbers 1, 2, 3, and so on cannot be pre-images of x. Okay, so let's actually draw a table which will indicate this idea more clearly. So let's look at an example. Okay, so maybe we have n, and then you have the surjective map f of n. Okay, and let's look at all the values that it maps to. Okay, so for instance, 1, let's say, is mapped to some number, let's say 3, 4, 5, 1, and so on. Okay, the number 2 is maybe mapped to 0.87, 9, 0, 0, 0. So on. Then 3, let's say, is mapped to 0.9, 1, 4, 3. Okay, and so on and so forth. Okay, so we will now construct a new, we will construct this number x, and we will construct it in a way that ensures that, f of 1 is not equal to x, f of 2 is not equal to x, and so on. Okay, the way we'll do this is by saying, well, let's consider the ith decimal place of f of I. Okay, so we will choose x so that the ith decimal place of x, okay, differs from the ith decimal place of f of I. Okay, so the ith, right, we'll just write it here, x is chosen such that the ith decimal place of f of I is different from the ith decimal place of x. Okay, so we just keep constructing it, digit by digit. Okay, and in fact, each time we will choose. In the ith step, we will choose the ith decimal place of x, and this ith decimal place of x will only be chosen between, for a reason that I will come to later, will only be chosen between the digits 1, 2, 3 up to 8. Okay, so 0 and 9 are excluded. Okay, and we will choose the ith decimal place of x just so that it is different from the ith decimal place of f of x. So for instance, here, the first decimal place should be different from 3 because that's the first decimal place of f of 1. Similarly, the second decimal place should be different from 7. The third decimal place should be different from 4, and so on. So for instance, I can pick x to be something like 0.46, 5, and so on. Okay, good. Now, so what's the advantage of this construction? By construction, okay, if f of j is equal to x, okay, and if it were a surjective map, then x would have some number j such that f of j is equal to x. Okay, then we see that f of j and x differ in the jth decimal place. This is just by the way we constructed x. Right? For every I, f of I and x differ in the ith decimal place. Okay. So so this yields a contradiction. Because suppose j is a number so that f of j is equal to x. Well, we know that they actually differ in the jth position, so they cannot be the same. Okay. There is one small caveat in this proof, and which is that, in fact, two real numbers, let's say x and y, can be the same even if they differ in their representations. Provided, if you have something of the form, x is just a bunch of digits, okay, followed by 1, 0, 0, 0, 0, 0, 0, so on. Okay, let's say, and y is, the same set of digits, okay, followed by 0 and then followed by 9, 9, 9, 9, 9. Basically, a bunch of trailing 9. Okay, so these two numbers are actually the same, okay, even though they have different representations. But really, in our construction, this cannot happen. Okay, so and the way we ensured this because we picked the digits of x to be only from 1 to 8. Okay, there are enough digits to ensure that from 1 to 8 to ensure that it is not equal to a specified digit. Okay, so we could always just pick these digits from 1 to 8, and in that case, you don't have this issue properly. Okay, so this actually completes the Cantor's theorem. Okay, so remember what we did. So we said, well, suppose there was a surjective map from natural numbers to real numbers. Well, we constructed this real number, which is again inside the range. Earlier we picked the set B, which was inside the range. Similarly, here we are going to pick a natural number, which is inside the range. In fact, between 0 and 1. Okay, and we picked it in a very special way. We picked it to ensure that the ith digit of this number x differs from the ith digit of f of I. Okay, and so really, so this is actually where this diagonalization comes in. The term diagonalization comes in because you see that this really forms a diagonal. Okay, that we are ensuring that these are unequal. And just by construction, you reach a contradiction because if there was a j, a natural number j, such that f of j is equal to x, they both have to differ in the jth bit. And this gives you the contradiction. Good. Now to summarize, in this video, we looked at diagonalization, this technique called diagonalization. We first defined what a power set is for a set. And we showed that even for infinite sets, the cardinality of a set is strictly less than the cardinality of the power set. So in particular, the cardinalities are not the same. And we showed this by using diagonalization. Okay. And then we also proved that we proved Cantor's theorem that says that the cardinality of natural numbers is different from the cardinality of real numbers. And we showed this using diagonalization. Thank you.